Welcome to the FCTV podcast. Ryan Harring's my next guest. His 20-plus career has tracked the evolution of modern computing, from servers and cloud infrastructure to quantum technology. After years working with companies like Dell and Hewlett-Packard Enterprise, he's now at IonQ, where he's helping build partnerships around quantum computing, what could be the next major leap in technology. Ryan, welcome to the podcast.
Thank you, Maggie. Thanks for having me.
Yeah, so let's get into it. But the first thing I want you to answer for us is what is quantum computing? Because I don't think everybody, including myself, really understands it. So just give us a brief little, what is it?
Sure. So quantum computing is the next evolution of computation. And what that really means is that we are taking the very fundamental principles of quantum physics and we are leveraging them to build a computer around them. And we're taking advantage of those fundamental principles to then do calculations to come up with answers that couldn't have been solved otherwise with a classical computer. And so the three main principles and the fundamental principles that we're taking advantage of are interference, superposition, and entanglement. If you'd like, I can tell you what each of those three mean really quickly, but I'll leave this up to you.
The basic gist, right, about quantum physics, quantum computing is it's just like computationally like way faster, right?
Super fast. Yeah. I mean, you could think of a classical computer calculates things in zeros and ones.
Okay.
With a quantum computer, though, you can calculate in the zeros and ones, but the reality is you can look at everything in between 0 and 1 at the exact same time. And what this does is this gives you a probabilistic answer that you otherwise couldn't have gotten with a classical computer. But you can only scan that space because you are leveraging the principles of quantum physics.
Okay. So what is IonQ and what are you guys doing?
Yeah, so we started out, we've been on a heck of a journey, right? So we went public back in 2022, but IonQ first got started back in 2015 with Dr. Chris Monroe and Dr. Jungsang Kim. And they are both from the University of Maryland and then University of Duke. And so it's interesting because in 2015, they had written a scientific paper. There was a capital venture firm that picked up this paper and they read through it and they actually approached these two professors and said, hey, we think this reads like a business plan and we want to give you $5 million to go and build this quantum computer idea that you have. And so that's what they did. So between 2015 and 2022, they spent a lot of time figuring out how we can build a primitive quantum computer, how we connect this primitive quantum computer to all three cloud platforms. And then, oh, by the way, we want to go ahead and take this quantum computing company public. And so they did that in 2022. We were the first full stack quantum computing company to go public on the New York Stock Exchange. We are currently trading under the ticker symbol IonQ. And we're probably about, $49 a share right now with a market cap of $14 billion, depending on the day. So that was our primary focus, is building these full stack quantum computers. Niccolo Diamasi, who's recently taken over as the CEO of IonQ, decided that, hey, we really need to diversify the portfolio because there is more than just quantum computing in the quantum space, and we want to be a platform company. We recognized really quickly that if we wanted to network these quantum computers together and grow them by scale, that we were going to have to get into the networking space. And so we purchased a quantum networking company. We went on to purchase another quantum security company. We purchased a satellite company because we want to do ground to satellite communications in a secure fashion. We also purchased another quantum computing company. And so we've just been on this tremendous tear over the past year trying to consolidate these technologies under one flagship.
So, all right. So let's slow down here for a second.
Yeah.
So why is that important? Why, and that kind of relates to why is that important to fiber broadband? Why do you need the networking piece to go with the quantum piece?
That's a good question. So the networking piece is really important primarily because quantum computers today, at least the ones that we're focused on, work off laser tables, right? So we're shooting lasers at atoms, asking these atoms to provide us some kind of an answer in return, right? In order to scale outside of the trap itself, you would have to essentially find a way to interconnect multiple computers together, similarly to what you see in in classical computation, right? Like it's totally disaggregated. In order for you to have, 6 computers that are working together with all their processing power, all their memory, all their GPU power, you sort of bring them together through a fiber connection. With quantum computers, it scales a little bit differently on the fiber side. And so you have to have specialized equipment from a quantum networking perspective that will allow and grow with the scale of the actual quantum computer itself. And so when you think about growing and scaling these systems and distributing, the compute across multiple, locations, fiber is seen as a similar sort of backbone architecture, just like it is on the classical side, right?
Okay.
So they
But
just
we're
haven't
talking
converged.
about, like, I would imagine like crazy amounts of data, though. This is like way more than what you would see on the classical computing side.
Yeah, well, so you can scan a larger data space, right? So from that perspective, yes. But if you're talking about like connecting a quantum computer to a network, you're going to have to figure out ways to connect each one of these little tiny atoms to a fiber strand and then move information across that space. But if you're trying to calculate a massive amount of numbers, all that needs to be done somehow, right? Fiber is the only way that we can do that as we know it today.
Right. So this is still an emerging technology, right?
Absolutely,
Right.
yeah.
So, I mean, what industries are we seeing that are going to be leveraging quantum computing? Where are we going to see it first?
Yeah, so actually you're already seeing it today.
Okay.
If you believe in the McKinsey reports and the BCG reports that are out there, and you follow any of those from a quantum perspective, you'll recognize that there are a lot of dollars that are being thrown around in this space. So by 2035, I believe that McKinsey report suggests that there is going to be roughly $3 trillion of economic value that's generated from the quantum technology space. $2.7 trillion of that money is primarily going to be on quantum computing, but then all the other quantum computing technologies sort of make up the other $300 billion worth, right? And so what that means is that there are some near-term benefits and near-term gains that some certain corporations and certain industries will be able to see. So if I think about, optimization, for instance, optimization is a general term, but there's an optimization problem in every single industry vertical out there, right? So energy, for instance, trying to figure out how to like transport energy in the most optimal way is a big deal. Cargo loading, believe it or not, is a big optimization problem. How can I pack an airplane with boxes in a certain configuration so maybe I can touch down, one less time in my travels?
So that's something that you would want to use quantum, like regular computing can't do that?
No, it can't, because the combinatorial problems are too big for a classical computer to solve efficiently. That's the key, right? It's all about efficiency. And quantum computers can do, a search space between the 0 and 1 so much faster that it can get to an answer more optimally than a classical computer can get to, right?
Okay.
And so as these combinatorial problems grow in size and the complexity of the problem grows in size, a quantum computer can supplement some of the knowledge transfer for classical computation.
Okay, so aside from like packing planes more...
Sure. That's a generic one.
Right,
like autonomous vehicles are another one. So
Okay.
we're working on route optimization. You can think of a UPS or a FedEx, right? If they could take, one less left turn on let's say across 10,000 trucks, and you can save 1% efficiency in the gas, let's just say, of these vehicles, then those small advantages really move the needle on from a financial perspective, right? And that's kind of what the power of quantum computing can do. But outside of that, you could think of any natural sort of problem in the world.
What about like curing cancer? That seems to be the one that I really think sounds like it would be the most important.
Yeah. We are working with some healthcare industries to start trying to figure out like how is it that quantum technologies can work on these problems. ANSYS is a healthcare provider, drug discovery provider that we're working with, and so yes, these are the problems that we want to solve. The most classically challenging, complex problems are what quantum computing technologies are really going to drive answers to.
So the other big technology that everybody's talking about is AI. So like where does AI fit in with quantum computing, and like once those two things get hooked up, like is it like lights out for humans and that's it? No need to be here anymore.
AI is interesting. So AI is very good at post-processing and pre-processing of data. Okay, and it's done very good, and it's expanding like crazy, right? But there are some things that quantum computers are going to do better at than the AI. So in between that post-processing and pre-processing, you have work to do. And let's just say you've got a stream of bit code that's moving down an AI string, and you get to this really hard, challenging problem that the classical computers have to sit there and crunch on. Well, that crunching time takes a lot of energy. It takes a lot of resources. It takes a lot of time to do. And frankly, some of the largest problems, those AIs can't really figure out. So what you can envision is a hybrid approach, let's just say. So let's say you are going down this bit stream and you get to this really classically challenging problem that the AI is having trouble crunching. Well, instead of sitting there crunching through the problem, you can take and you offload that information over to the quantum computer, let the QPU do the calculation, and then bring that answer back into the bit stream and then continue down. You get to another classically challenging problem that the QPU or the CPU is going to have to crunch on, and you do the same thing again, right? So it's a constant iteration between the actual classical computation and the quantum computation. But at the end of the day, the hope is that there will be a better result that appears through that process.
So you're making me think about, there's also lots of talk about these hyperscalers, right? These mega data centers that we're going to need for AI. Does quantum computing help maybe? Are you not going to need so much CPU power, and therefore you won't have the energy drain? You won't have a lot of the environmental impacts that folks are talking about. Is that possible?
You're thinking right.
Am I thinking the right way?
You are thinking the right way. Yeah. So I work pretty closely with some national labs, and this one specific national lab I spoke with said that they can create 5 large language models a year the size of ChatGPT with their supercomputer that they've got in their facility. But this comes at the cost of about 5 megawatts of power per large language model. And this is a fantastic drain on energy resources for the grid, right? Our grid is not in a place that it can really do. I mean, it can do those things, but there's got to be a more optimal way to do it, is what they're thinking. And so if you think about XAI, they've set up a data center farm out in Memphis, Tennessee. And this national lab is really trying to compete with what it is that XAI is doing. XAI can throw a bunch of resources at their problems, where the national lab has to rely on taxpayers' dollars. So what they want to do is, instead of trying to throw more dollar resources at the problem, they want to figure out how they can leverage the power of quantum computing to drive out some of these inefficiencies of the development of these large language models, right? But it all derives from the fact that, hey, how can we use less power? How can we think about our environment around us when we're developing these data centers? Is there a way that quantum computers can sort of help us solve these problems? And the answer is yes. You just need a bunch of smart people to sit down in a room and start trying to solve that actual problem.
All right. So when are quantum computers going to be? I mean, again, we're saying it's a future technology. You guys are already here doing it, but when is it going to be more out there, more ubiquitously used?
Yeah, that's a good question. So it's definitely being used, but I think what you're looking for is fault tolerance. Fault-tolerant quantum computers are still a little ways away, right? But
what does that mean? Slow down. I don't know. Fault-tolerant. What's that mean?
So a fault-tolerant quantum computer is just like a fault-tolerant regular computer, right? So if things break, you can just immediately pick back up and compute again.
Okay.
So right now you have to tune lasers to make sure they're aligned with atoms. You have to regularly bring the system down and then bring it back up, right? So if you're thinking about a production-ready environment, that's not a very effective way to go about your day-to-day activity, right?
Right.
So fault-tolerant quantum computers are coming, but they're not here yet. In fact, we are accelerating that roadmap. So IonQ says that they will have 80,000 fault-tolerant logical qubits by 2029. And this is important for a lot of different reasons, but one that I'll name here is that there's this thing called Q Day that's coming up. Maybe you've heard of it. Maybe some of your viewers or listeners have heard of this. But Q Day essentially says that, hey, eventually what's going to end up happening is quantum computers are going to be so good at their tasks that they're going to be able to start breaking RSA encryption. And so there are global adversaries that are doing this thing called harvest now and decrypt later. And so harvest now and decrypt later just means that they're going to scrape all this information that they
Scary
can.
stuff.
It is scary stuff. And I don't want to come off as an alarmist, but this is something that everybody's watching and trying to keep an eye on, especially in my space. But harvest now and decrypt later gives an adversarial network an opportunity to come through, and when quantum computers are good enough, to break the codes that are housing that sensitive information. And if you think that, between now and then, 4 or 5 years away, there's going to be a quantum computer through our accelerated roadmap that's going to be able to break those kinds of encryptions, it's got a lot of heads turning, right? So this is a compelling event. Fault-tolerant quantum computers are coming. You have to be able to not only build them, but then also safeguard against them at the same time. And that's going to be very important for not only this industry, but federal governments and friendly nations across the globe to pay attention to and try to solve for at the same time.
Yeah. I'm going to pivot a little bit here.
Sure.
You were talking about states like Tennessee are really looking into how to leverage quantum computing to do some stuff there. Tell me about the workforce development and what does that mean to what kind of workforce do you need to be able to run quantum computing and quantum computers and what can policymakers at the state level do to encourage that?
Yeah, so Tennessee is really leaning in on the quantum front. As you know, EPB, the Electric Power Board at Chattanooga, they've got this first mover DNA that's really exciting and very inspiring, right? And
Chattanooga is a cool town.
It is a pretty cool town, and I feel like their infectiousness is sort of caught the state of Tennessee on fire. So that's fantastic. They've got this great electronic distribution, electric grid process that's going on. I can't even talk about I don't even fully know what they're doing on the electrical grid side, right? They just got some cool electronics that are built in. Plus they are fully invested to fast fiber connectivity, which is important.
Right.
They created the nation's first commercially available quantum network. And then of course they decided to partner with IonQ to bring the nation's first Forte enterprise into their data center. And so now they've got this infrastructure that includes a quantum network and a quantum computer, partnered with IonQ, and that's very exciting. And it's all about driving community benefit, which is also very exciting. But I think some of the nuances of the partnership that don't always bleed through. Yes, these systems are big and flashy, but we're also working very closely with them on workforce development. And so workforce development is key, right? Just like many industries. In fact, I was just sitting on another panel and they were talking about how there is a lack of picks and shovels and people who can actually manage and control and install fiber just across the U.S. While we're not in the fiber business, we can totally relate to that situation because we are lacking quantum talent. And it's not just the physicists, it's not just the engineers, it's the business development representatives, it's the customer success representatives, it's the application developers, it's the lawyers, right? In order for us to really push this industry forward, we're going to have to find ways to bring people up to speed who are already in the industry in adjacent areas that can understand what's going on. And so EPB understood this, and they've decided to work with IonQ to find 10 local individuals from the community, bring them into EPB space for a year, give them a stipend of probably shouldn't say how much money that they're giving them, but give them a stipend so they can learn EPB's business model, and then also start looking at EPB's problems through the lens of our trapped ion quantum computer that's there on site. So they're teaching them a core set of values. We're teaching them a core set of values so they could be more valuable to not only EPB and IonQ, but then also the community members as well.
Yeah.
And so this
cool.
this is very important.
Yeah.
So as far as the state's concerned, though, Governor Bill Lee back in February said that he wanted to earmark $20 million in the 26-27 budget to focus on developing quantum technologies in the state, which is fantastic. They sent that to legislature. Legislature actually said that's not enough money. We're going to add another $23 million on top of it. So now the state of Tennessee is working with $43 million worth of funding to help deliver some kind of quantum advantage within the state of Tennessee. We're working through the nuances of what that's going to look like.
Yeah.
But it's very exciting times.
Yeah.
And I think that, Tennessee, while some may think it's a smaller state, is really leaning in on the quantum front. And a lot of that is because of the work that EPB has done.
Yeah, that's great. That's great. So as we're wrapping up here, I just want to kind of give you the last word. If we look like 10 years from now, what is quantum computing going to mean for the average person, sort of in their? Are we going to see major differences in applications or things?
Yeah,
Yeah.
so if you think 10 years out is a long way, but I guess it's not that long,
It's
is
not,
it?
I
I
mean,
don't
felt like
know.
it was just yesterday. It was 2016. Come on.
That's very true. I'll summarize it like this. You have your cell phone. Now, we all have a cell phone. Mine's not with me right here, but I have no idea what's really going on underneath the hood of that cell phone. I mean, I have some idea, but I don't have a deep understanding and a knowledge of what's going on in that actual phone itself. In the quantum computing space, we haven't extracted to the level yet to where we don't have to know what's going on under the hood. It just happens. So if I were to say in 10 years, I believe that disaggregation will happen, right? Like quantum computers will be running in the background doing stuff, and you're not going to know that it's superposition or entanglement or interference that's happening. It's just going to happen. So I think that's going to be a
Great.
big change. That's where I
All
think
right.
we'll be. Yeah.
I look forward to it.
Yeah.
Well, thanks for joining us here on FCTV, and let's meet back here in a decade.
Absolutely.
Yeah.
Let's not wait that long, but absolutely.
Okay. Yeah. That might be too long, but thanks a lot.
Thank you.